Hello everyone, this is Finnerpind speaking to you from Treble HQ in Reykjavik, Iceland. Thank you all for tuning in here today. I think we have a very exciting 1.5 hour ahead of us, both some very exciting additions and improvements to the Treble software, as well as great presentations from both Arup and L-Acoustics too. So for all the kind of acoustics nerds around the world, present company included, I think I can safely say that it's going to be fun. And I think I'm just going to dive right in because there is a lot to show and discuss, so let's use the time effectively. This is our biggest update ever. And the agenda for today is that first I will be introducing some major new feature additions. This will take approximately 20 minutes or so. Then we will give the word over to Arup, who will talk about their experience using the Treble software. I will then take the word back and show a variety of smaller but very important additions and improvements, mostly sort of quality of life improvements. Then L-Acoustics takes over and talks about their experience with Treble on a very cool case. And finally, I'll spend a couple of minutes to talk about some exciting new partnerships and an updated licensing model. And then we should have ample time for questions or Q&A after all the presentations. Before I dive into all of this, I want to take a few seconds just to give credit and acknowledge the absolutely fantastic team here at Treble that has been working extremely hard for a long time leading up to today's event. Treble Technologies is not just some kind of nameless company. It's actually just a group of these people, well, these and a handful of others who couldn't make it in on the office when we took the photo. But anyway, this group of very passionate, brilliant and kind scientists, engineers, developers and entrepreneurs who come to work almost every day with kind of the goal of just trying to have a positive impact on the acoustics community, trying to build tools that can help designers and engineers push the agenda of acoustics, work more effectively, do cool things, have more fun, and sort of ultimately leading to hopefully a better sounding world, which is our vision here at Treble. So Treble is a true passion project, and all the credit goes to these fantastic people that have been doing some great work, in my humble opinion. Sorry, I just had to start there because I love these guys so much. Anyway, the Treble platform consists of 3 main components. The centerpiece is the cloud-based simulation engine. And then we have built 2 interfaces, 2 products towards this same engine. On the one hand, what we call the application, which is a graphic user interface software. And on the other hand, the software development kit, the SDK, which is a programmatic interface to the simulation engine. And today I will be exclusively talking about the application side of it. And these updates we're announcing today have to do with the application. But I want to spend 30 seconds just to announce that just in 3 weeks, we will be having another webinar with another major update to our other product, the SDK. And I encourage anyone who's interested to tune into that as well. The SDK is an extremely powerful piece of software that is very suitable for a variety of use cases, advanced R&D related use cases, such as running high-fidelity acoustic simulations at scale to generate large data sets to then train all kinds of audio machine learning algorithms, also to evaluate the performance of audio machine learning algorithms without having to rely on measurements and so on. For product virtual prototyping, being able to virtually prototype in different acoustic conditions in an automated way and so on. Parametric analyses and automotive acoustics as well. So anyone who's interested in that, I really encourage you to tune in 3 weeks. But let's now turn our attention to the application, this GUI product, which is tailored for architectural acoustics, sound system design, and other acoustics related things. The application, like the SDK, is powered by this proprietary sound simulation engine that we have built, which we are very proud of, which merges wave-based modeling at low frequencies, very accelerated wave-based modeling, and then sort of state-of-the-art geometrical acoustics for high-frequency modeling. This, combined with a plethora of advanced both pre- and post-processing features, comprise a very powerful tool in the toolkit of people working with acoustics. Now, we released the application almost 2 years ago. We deliberately went out with the product a bit early because it is a fundamental principle here at Treble to sort of build these software tools in collaboration with the acoustics community. We wanted to go out early to get the feedback, good and bad, to get the prioritization, to hear what's important, what's not, where we should put our emphasis and resources, and sort of iterate on this together with the community. And now, over the course of the last almost 2 years, we have added a whole range of features. I'm showing some of the major things here on the slide, sort of continuously over the course of the last 2 years. And along with these kind of major additions that I'm showing here, there's also very many kind of smaller but important improvements along the way. And we are very proud now to have reached the point where this application is being used by more than 150 organizations across the globe to really kind of put acoustics on the next, or get to the next level when it comes to acoustics. And it's inspiring to see it being used in real-world cases around the world. The core technology and the software has been validated in a whole range of all kinds of validation studies and benchmarks and so on, and I encourage anyone who's interested to take a look at that. That can be found on our website. And this means that we have reached the point, and I would say especially after today's big update, where we have a very powerful offering, which we really hope benefits the acoustic community, that has some very unique features and capabilities and a unique value proposition relating to the cloud-based nature of the product, the unprecedented accuracy as validated in many benchmarks that our simulation engine can offer, a huge emphasis on improving the workflow so that people can be spending their time on acoustics and not on tedious manual labor, collaboration with colleagues across the globe via the browser as a modern software should be, taking oralizations to the next level, making them more immersive, and then combining this with an attractive pricing model, being able to operate this at any scale, and of course a huge emphasis on the highest possible security and adherence to the strictest cloud security standards. Okay, that was the short intro. Now we should all be on the same page about what Treble is and so on, and now we can dive into the good stuff, which is first the major new features that we are announcing here today. The first one, which is, in my humble opinion, simply the coolest thing I have seen when it comes to acoustics for several years. I think it's the coolest thing I've seen since I first saw a wave-based acoustic simulation run on a GPU, which was in 2015 or something like that. This BIM importing functionality, which includes automatic space extraction and automated geometry simplification. I will then go on to show forced modal analyses to visualize room mode behavior at low frequencies, and then show our enhanced post-processing capabilities relating to complex source summation. So let's dive into the first aspect, which is the BIM, or the IFC importing. Now, we have spoken to a lot of people, a lot of consultants, engineers and designers, people who work with architectural acoustics, and we consistently hear that one of the biggest pain points they face is the very time-consuming process it takes from going from rich, complex, detailed architectural models, like the one I have on the screen here, for example, to simpler models which are suited for simulation. And often in projects, more than half of the time goes into this geometry cleanup step. And this is something that we set out to address here in Treble. More than 2 years ago, we built a dedicated team around this challenge. And now we are introducing an automatic process that can take complex BIM models and automatically split them up into separate spaces and automatically simplify them and make them suited for acoustic simulations. I think this will be a massive workflow improvement for our users so that they can spend their time more on acoustics and less on 3D model cleanup. Now, I will say already now here in the beginning that this is a very challenging task to develop an algorithm that can do this task for us. And the sort of edge case space is very wide. BIM models come in a variety of flavors and so on, and there are so many imperfections in them and so on. So in some cases, this algorithm works perfectly. In other cases, it works very well, but not perfectly, but it will get you maybe 80–90% of the way to a simulation or simulatable model. And then the process would be that you import it into Treble, get it automatically simplified, pull it back to SketchUp, do the last finishing touches of the cleanup, and then back again into Treble. And I will show kind of both cases now. I will start with a more simpler model, which is also just a bit more kind of cleaner way to demonstrate the process, show you how I go through the step of importing it, having it separated into spaces, simplified. Then I'll quickly set up a simulation and actually an oralization, just to kind of show the whole workflow and how quickly one can go from a BIM model to simulation results, essentially. Then I will apply it on a more complex model, actually this model I have here on the screen, where we will see that the algorithm does a really good job of separating it out into spaces and simplifying it, but it's not entirely perfect, so I pull it back into SketchUp, do the last finishing touches, and then I'm good to go. So let's dig in. Starting with this bit simpler model, it still has a lot of geometric details. I mean, look at these railings here on the stair. Look at the legs on the chair. There's holes between the windows and the walls and so on. So typically, up until now, the process would be to kind of start from scratch, drawing this model up in SketchUp or Rhino or something like that. But now I'm going to import it into Treble and work with it directly. Here I'm opening up Treble. It might look a bit different for people who have used Treble in the past because we're also overhauling the look of it. I'll come back to that later, but now I'm just going to show here. I go to import geometry. I have this IFC file, this BIM file on my computer, and I simply drag and drop it here and press upload. Now this gets shipped to the cloud and the geometry algorithm takes over and starts splitting it up and simplifying it and so on. This step does take a couple of minutes because it's a very complex task that's happening under the hood. So just in order to save some time, I already started an upload a couple of minutes ago, so I can show you here once this is done. Then I would be faced with this view here where I can see the different spaces within the model. I can see that details have been simplified. For example, the railings are gone now. And I'm ready to import this into a project. I'll just create a new project here. And I'm good to go, essentially. I've already run a couple of simulations in one of these spaces here earlier, just to save us some time. Let me show you quickly how that looks and how we can oralize one of these spaces. So we'll go into a different project here and open this up. So this is the kind of attic living room space. It's been merged into one model because it's acoustically coupled, these two spaces here. You can see how the railings are gone, the chairs look much simpler, it's watertight, so the holes here between the windows and the walls are fixed and all of that. I went through the regular steps of first assigning some materials, throwing in a couple of sources and a few receivers and setting some settings. This setup step took me maybe 1 minute, and then I ran the simulation that took around a couple of minutes to run, and I'm basically ready to explore some results. I simulated it with and without some acoustic treatment. And we can see here that it's more reverberant without this acoustic treatment I put in. And I could, of course, explore all kinds of results and so on here in the results view. But instead, I'm also just going to quickly listen to the space. So I go into our oralizer, where I can put up the comparison between the two cases I simulated. I add some sounds on the sources here, maybe some group dialogue, for example, onto the two different sources, like so. And then I can simply jump into the space and I can hear how it's going to sound with these two conditions. And then the icing on the cake, I could click the share link here, call it design proposal or something like that, and then generate a link to this listening experience, which I've done now. Share this link with, for example, my client, like so, and the client, she could just go receive the link. She doesn't have to be a Treble user or anything like that, and she can just experience the listening experience like so. So I've kind of shown going from a BIM model, having it automatically simplified, prepared, separated into spaces, a couple of minutes of setup to run the simulations, and then a listening experience on the other hand, the whole thing taking around 10 minutes maybe or something like that. I think this, well, at least I think it's very cool. Let's now apply it on a more challenging case, a very rich BIM model and complex, large and so on, which we see here. I have already imported it just to save us some time. This time the importing process took a few more minutes than for the smaller model as expected, but still nothing too bad, just a few minutes. And it successfully separates this big office model into several spaces, and they've been simplified and so on. So let me show you here. This project is over here. It's around 75 spaces in total that are within that model. And I'm first going to show you this cafeteria space, which the initial import looks like this. A lot of details have been simplified. Again, look at, for example, the furniture in here. This model is ready for a simulation. However, the simplifying algorithm did not do a perfect job. Note, for example, that there's a little bit of junk outside of the model here. And the model in this case was not perfectly watertight. So this means that I can only run a GA simulation on it right away. But still, that's a very impressive feat, I would say, importing this very complex model, automatically separated, simplified, and GA simulation right away. No manual labor needed. But if I wanted to go the extra step of running a wave simulation on it, what I would do is I would go back to SketchUp, fetch the model into there, do the last touches on the cleanup, and then re-upload. Let me show you real quick. Now, here I am in SketchUp. The Treble plugin is open. I just click this Fetch Geometry button. I find this project and the space in question. And this is the initial import from the automatic algorithm. I get it here into SketchUp, and then I can do the last finishing touches like deleting these extra things out here, finding out where the hole is, plugging that up. Took me around 10 minutes to do the final cleanup. I used the checking algorithm to help me find the issues in the model, and then I re-upload it to the software, and we can see the watertight cleaned up version here. So, complex, large models, no problem. The algorithm gets me, in this case, 80–90% of the way, and I do the last touches here. This was a relatively small model, or sort of small space within the model. Let me show you an example of another one, which is much bigger, where the algorithm, let's see, where is this? here we go. This is a big atrium spanning several floors, connecting corridors and so on. It would probably taken me a couple of days to build an acoustic model for this from scratch, but the algorithm did this automatically for me. It merged several spaces within the BIM model because they are acoustically coupled, and I can immediately run a GA simulation on this without any extra work. And like before, if I wanted to do a wave-based simulation, some minor finishing touches would have been needed here. This algorithm, this automatic simplifying space extracting algorithm, will only get better and better with time. I will also mention that as we train it on more and more models. Okay, this was the quick intro to the BIM IFC importing automatic extraction simplification process that we have built. We really look forward to putting this out to the world and getting feedback, and we certainly hope that it will make the lives of people working with acoustic simulations more fun, more effective, and so that they can spend their time on acoustics and not on geometry cleanup. Okay, what we just showed was a big workflow improvement. What I'm now about to show is something very different, which is an advanced analysis feature relating to low frequency sound and being able to visualize and control and analyze sound in rooms at low frequencies, which is often a big challenge. And I'm going to use this studio project here as a sort of test bed for this new modal analysis feature. Let's just first spend a few seconds to familiarize ourselves with this room model here. So it's, I'm just going to turn off this thing so we see it a bit better. It's a sort of typical studio space, a relatively small room with critical listening space. And I've already run a couple of simulations, one which I call with less treatment and another with treatment, so kind of comparing two different acoustic designs of this space. And I put in a couple of Genelec monitors here, and then a couple of subwoofers from D&B here as well. Then I put in some listening positions, mixed position, sofa, and at the piano. And I also put this surface receiver, which is sort of a way to visualize sound or acoustic parameters and so on across space. Maybe before we just start looking at the room modes and the room mode behavior at low frequencies, we can maybe just for fun listen to the space for a couple of seconds. So I'm gonna put here a song, which I like, a Fleetwood Mac song, into the different speakers. So the left and right channel of this Fleetwood Mac song go into the Genelec speakers, and then the mono channel goes to the sub, like so. And then we can jump into the space and hear how it sounds. And with more treatment, it's a bit crisper, a bit clearer. Jump between different positions. Try hearing with and without the sub. The kick drum is much thinner when we mute the sub, and so on. Anyway, that was just for fun. Let's now go and look at this new feature, which we call forced modal analysis, which if I enter here the surface receiver view and forced modal analysis, I can see how the room modes vary in the space from different sources that are exciting the room, with the goal then of analyzing this and trying to get an even response in the room and so on. So maybe if I select this subwoofer here, number one, and then we can sort of maybe control the range here a little bit, something like this, and then we can sort of scroll through the different frequencies at low frequencies and see how this varies here, the room mode behavior at low frequencies. Very cool, and I can select any point on the grid here to see the frequency response. So for example, if I'm interested in studying here at the listening or mixing position, I can see that, but also in other positions, obviously, in the space, and then sort of iterate through this. So I think this is a very unique and powerful feature of Treble, being able to visualize these room modes and really dig into the low frequency behaviors of rooms. And of course, this is made possible with our wave-based simulation engine. I'll come back to this a bit later and show some more things in this model and take this a bit further, but let's park it for here. I think it sort of speaks for itself to some extent, this feature, and it's something we think is very cool. Okay, the next feature relates to complex source summation. That is, being able to, in post-processing, after the simulation is run, to add up different responses from different sources, sort of after the fact. And this obviously is very important for analyzing, for example, PA systems in space and just the combined response in a room from many sound sources. And I want to start by demonstrating this at the very kind of fundamental level, just to showcase some of the nuances around this. And then I will move to a very large and complex case and show it also in action in kind of more practical setting. So I've set up here a very simple simulation, which is essentially a free field simulation because it's a very big box and I just simulated a short amount of time. There's one receiver and kind of two sources a bit different distance from the receiver. And we see this kind of pulse from the two sources fly by this receiver, and that's all we have in the response here. And in the frequency domain, this looks something like this. It's an omni source with just a flat spectrum. So we can see here the level of the two sources and the same amplitude across all frequencies. This was a hybrid simulation where the wave-based was up to 750 Hertz. Now I'm going to sum the response from these two sources. I would do that by simply clicking Sum Sources here, check these sources that I want to sum. These can be as many sources as I want. Click the sum button, takes a couple of seconds, and then I get back a new source which is summed. I've already done it here just for saving time. So what we see here, if we look at the summed response, we see here this strong comb filtering effect from the two waves interfering at certain frequencies, kind of in a destructive way, to reducing the amplitude and increasing the amplitude, constructive interference at other frequencies. And this kind of highlights the sort of phase-based nature of both treble solvers, both the wave-based but also geometrical acoustics. You see here, this is where the transition frequency is, that it just kind of very seamlessly preserves the phase as it goes from the wave-based over to geometrical acoustics. So this kind of shows how you could, obviously it's just some sources, but also kind of how this intricate nature of the different contributions are preserved across the frequency range. This was at the very most fundamental level. Let me quickly show you another similar fundamental case, just not in free field, but actually closer to a boundary, so we just see like a single reflection. We can see the direct sound and then a single reflection. And I've simulated this for two different material properties. One which is just a flat 50% absorption, and another one which has some glass wool properties, which will have different absorption properties, but also different phase properties. And I'm trying to show you here that if we then look at the response of these two different reflections, or sort of same reflection but hitting a different type of material, we see that the positions of the peaks and dips has been changed because of the phase response of the material. So this is just to highlight the kind of, again, the phase-based nature of treble and the improved accuracy you get for example, very important early reflection modeling and oralization for perceptual quality and so on. And then this certainly kind of continues if we would look at summed sources. So here for these two cases of the different materials, we see if I have two sources and kind of hitting this wall and being reflected back, the frequency response is actually quite different due to both the amplitude response and the phase response at the boundary. This was maybe quite detailed and acoustics nerdism, but it's just to highlight that materials are modeled in a more precise way than what has been typically done in the past in treble, preserving not just absorption but also phase properties and also in the solvers themselves. Okay, now that was kind of very academic or sort of theoretical. Let's now look at a real case where we're going to sum a lot of sources. So I'm going to open a project here, which is called Train Station in Oslo. And this is a large model. It's around 30,000 cubic meters. And I've put in here 72 sound sources into the model. I've put these tannoy ceiling speakers all across the model. I'm going to hide the surface receiver so you see a bit better. So all across this model here are these ceiling speakers. So this would be a rather typical scenario of modeling a large infrastructure project like a train station or an airport or something like this, and making sure that the PA system can be heard. And I have, as I said, put in 72 of these sound sources. I put in a few listening positions if I wanted to do oralization, and then I put this very large surface receiver as well, which has around 1,000 grid points on it. And I've simulated this for 2 acoustic conditions, just for fun, as always, kind of more acoustic treatment, less acoustic treatment, so we can compare some results later. This kind of simulation takes around 5 minutes to run in treble for all the sources in this grid receiver. We tried running this in another kind of legacy acoustic simulation software. It took more than 10 hours there. So this is a great example of the kind of drastic speed up and workflow efficiencies you can get with using treble, because it all runs in the cloud, it all runs in parallel and so on. So this, and you can very quickly then iterate on designs of these kinds of projects. So let's take a look at the results. I've pre-run it once again just to save a little bit of time. And I am going to show you first maybe just these 2 conditions that I simulated. So one which I called reverberant V2, I was doing some iterations, has a reverberation time up to around 3 seconds in the mid-frequency range, whereas just over 1 second this treated case here. But I mainly want to look at these surface receivers and look at the combined response of this massive PA system that we have set up here. And I can, for example, look at sound pressure level here from a single source that we see kind of spread across the space, or the speech intelligibility that I can see how it varies across the space. But more interestingly, I can look at the combined response. And I've already clicked some multiple sources and then clicked this guy here, which selects all of them, ran it, took a couple of minutes, I got back this summed source, which I called all sources. And by the way, while source summing is happening, I can, as with everything in treble, I can just kind of leave it running in the cloud and go work on something else meanwhile. And let's compare the results here from this PA system between the 2 simulations. So overall, we certainly see that the speech intelligibility is lower in this reverberant condition compared to the treated condition, perhaps especially in this region here. We can, for example, investigate, let's see which areas have speech intelligibility higher than 0.5. See, that's quite well covered in this design I made of the PA system earlier, whereas this part here does not reach 0.5 in this kind of more reverberant condition. So I think this has kind of illustrated in a nice way the source summing capabilities, which we are launching now, but also kind of showing treble in action on a very large project and how efficiently it can run on such cases. Before I wrap up my talks about source summing, I want to go back to the studio model I was showing you earlier, and just quickly show you in the modal view how I can, of course, also sum sources there and look at the mode response from while two sources are exciting the room. Select from the same simulation, the one I called width treatment, and I'm going to compare one subwoofer versus the summed response from both subwoofers. I'm going to set the range here so it's the same when I'm flipping between the two, just to kind of be consistent. And then we can see here, this is sort of my take on it, not being an expert studio designer, but it appears to me that the response is a bit more even across the space at low frequencies when we have the two subs compared to the one. So if I sort of scroll around here, certainly there are dips and peaks, but it's still somewhat sort of a bit more uniform, whereas if I look at the single one, and especially sort of this part of the model, yeah, seems less covered somehow at low frequencies. But this is indeed for the designer to analyze and so on, and we're bringing the tools to be able to do that. Okay, let's park it here, and now we're going to give the word over to Arup, for their exciting presentation, and then I'll come back and show a collection of smaller but important additions to the software. Thanks.
Hello, we're here to talk today about oralization processes at Arup. My name's Shane Myrbeck, and I'm an associate principal in the Los Angeles office.
And my name is Willette, and I'm a consultant in the Seattle office.
So a big part of the reason that we're here talking about this in any respect is because of our sound lab. So we've run an oralization studio at Arup for over 25 years now, which is the sound lab. We have these in offices all over the world. There are over 30 of them now. And they all have different features and different loudspeaker setups and things like that. But the primary purpose of them and the origin story of them is for a dedicated purpose-built oralization studio. Over the years, they've evolved beyond just that. So there's the sound lab, which is primarily dedicated to oralization specifically. But there's also an experience lab, which kind of expands beyond sound to XR video and to even some haptic and olfactory elements in some cases. And then we have our M lab, which is the more portable version of the sound lab, which could exist on a project site or in a conference context or something like that. Key to all of these rooms is flexibility of software platforms. For the Sound Lab specifically, we tend to group things in three categories. We have the recording aspect, so we have a 3D recording process that we can play back and modify in some way to show design or various biophilic soundscaping concepts or music recordings. We have our modeling process, which is what we're going to talk about most today. The computer modeling process. And then we also use the platforms as a composition studio and for exhibit design because it's a 3D sound canvas. But all that to say that we need to use many different software packages to accommodate all these different use cases. And some of the projects that we do in there also span quite a variety of sectors. So these are half a dozen examples amongst hundreds of different projects we've oralized in the Sound Lab, from a reverberation chamber for a tour for Bjork, to museums such as the Paralympic and Olympic Museum in the US and Rafik Anadol's Dataland, to transit centers. This is the 2nd Avenue subway in New York, but we've also done high-speed trains in the UK and elsewhere. So it's a wide variety of projects, again, needing a kind of a lot of flexibility within the oralization studio itself. And one thing we're always looking for within the Sound Lab context is efficiency. So because we're using so many different platforms and so many different techniques, there's often a bottleneck somewhere in the process. So one thing that we've focused on over the past couple of years is trying to gain efficiency in our traditional process, which was taking a sophisticated BIM model or 3D architectural model and kind of modifying that 3D geometry to get into a traditional geometric acoustics software package, then taking the output of that and putting that in something like Max MSP to get the multi-channel output into the Sound Lab. one of the things that we love about the Treble software package is that it adds a lot of efficiency into that process. So I'm going to hand it over to Aaron now to talk about a few project examples that describe that.
All right, so I'm going to talk through a few case studies where we've been able to use Treble on projects recently, and this has been for both numerical modeling and oralization. So the first one that I'll discuss is the Perception Engineering Lab at the Salford University in the UK. And this is going to be a new ITU standard listening room where they want to do very precise analysis of how spatialization affects perception of sound. And so they're building this room to accommodate at least 50, potentially up to 120 different loudspeakers to do a really higher order ambisonic listening format. And we've been able to use Treble so far in just the early stages of the project where we are to track some early reflections throughout the space. So as I mentioned, there are going to be a lot of loudspeakers in this room, and because they want to be so precise about spatialization, you need to be really careful about early reflections blurring the image or shifting the image between locations that aren't exactly what you're trying to model. And so we've been following the standard guidance of tracking any reflections that are within 15 milliseconds of the direct sound and making sure that none of them reach within 10 dB of that direct sound. And so using Treble's reflection tracker, it's been really easy to kind of visualize exactly where all of these speakers are and where those first reflections are coming from. And we identified one, for instance, from a door that didn't have absorption in the initial design. We found some problematic reflections there, and now we can make the case for it. And this isn't brand new technology, but Treble's interface is so well organized and streamlined that it's easy to keep track of a really complicated system like this and track all of the potentially problematic reflections through the space. Okay, so next I'm going to talk about the project which we can see a little piece of here. This is an indoor sports practice stadium. And what you're seeing here is a piece of the ceiling geometry which has this complicated lattice. That's these structural beams that extend about 6 feet or 2 meters deep. And they're flush against the roof, which is this complex multidimensional curved shape. And the room itself is also quite a large volume, about 300,000 cubic meters on that order. So as you can imagine, this is a pretty tough problem for most room acoustic solvers to handle. So specifically what was so tough about this one is just modeling this complex geometry in a large space in a way that won't, make the software freak out and take a million years to process your data. So the architectural model we received with that complex geometry had a lot of little gaps and holes everywhere, which we all know usually acoustic solver software doesn't like. But to model it really precisely in a completely airtight fashion with those lattice beams being flush against the roof in every location was an extremely time-consuming process. And so what we did instead is we took something more similar to the architectural model where that lattice was floating just like a couple millimeters between the actual roof itself. And Treble accepted this geometry without really any complaints. And one of our more standard ray tracing software packages would accept the geometry, but would take about 42 days to produce results, which pretty tough to work with that. So Treble would run those same results in less than an hour. And so then we could run through all of our design conditions, get our numerical results, and eventually we were able to produce a really compelling oralization of some of the graphs that you see there, which are the reverberation time in the space if you don't have any absorption in the ceiling, or if you do, which in a huge volume space like this is so important. And so we were able to communicate that in our oralization, all reach a decision with the client, and it was a great success. Another interesting oralization that we've worked on was this event center presentation stage. And as you can see here, there are these architectural features on either side of the stage, which they were calling fins. And in the initial design, we noticed that these fins were basically just parallel flat surfaces perpendicular to the stage. And as a result, we noticed that there might be a problematic flutter echo between these. And that's a really difficult phenomenon to explain to a non-technical audience, and so we decided that oralization was probably the best path forward. So we threw together a quick treble model, put it in the binaural oralizer, and we could immediately hear the problem. So then we could propose some potential solutions, like either putting absorption on the faces of the fins or just rotating them upstage so that they aren't parallel to each other. And we presented this oralization both in person in our sound lab and remotely.
And this is one of the major breakthroughs in terms of the using the platform at Treble for its user interface. So for a long time, and this was exacerbated during lockdown when everyone was remote, we've developed various ways to do distributed team presentations. And sometimes, in years past, that ended up being just a fixed video that we would send off to people. But the hybrid presentation of being able to do ambisonics in the sound lab with binaural at home has been somewhat elusive. So in this case, what we had was members of the project team in the sound lab in San Francisco, some of the project managers and a few of the technical folks on the project. But then we had 4 people remote, and they were all of varying levels of technical expertise. So we had the audio engineer for the space, who is the highest level of technical expertise. Then we had the set designer, I would say the next tier, and then a person from Arup, and then we had the project executive from the client side, who had kind of no level of technical expertise within the context of what we were presenting. We were able to present the material in the sound lab with us running the interface and give instructions to all the people that were remote and have them navigate the web browser interface. Everyone went offline and listened for a few moments and then came back online, and we're all able to agree on the direction for the project within a few minutes. So in terms of a presentation interface, it was a step change and what we were able to do. One modeling technique that we've developed over a number of years, over a decade now, is this concept of acoustic wayfinding. So the gentleman pictured in the photo here is an architect named Chris Downey. He was a practicing architect for 15 or so years and then had a surgery on his brain that caused him to lose his sight unexpectedly. So since then, he's developed an architecture practice called Architecture for the Blind, where he uses acoustic wayfinding as one concept within a framework of universal design. So we've worked with him over the years to be able to try to model these concepts of acoustic wayfinding in the design phase to get buy-in from various stakeholders on projects to implement them on the projects that Chris is working on. So the tools of acoustics wayfinding is that you have your palette of acoustic materials, and this is something that's obviously known through the history of acoustic consulting. So you have your absorption coefficients, scattering coefficients, and project experience to be able to select various materials to create these acoustic moments that could provide some directionality and wayfinding elements. You need to take those materials and then develop an intuitive sense of spatial transitions. So, for example, the transition from cane taps on a concrete surface to a carpeted surface, transitions from a reverberant, corridor space to a more absorptive space. Asymmetry within spaces that can be learned. So, for example, absorption on one side and reflective surfaces on another side that you can kind of understand over the time that you experience a space and use that for navigation. All these are various things you can implement in a project that help with acoustic wayfinding. During the design phase, of course, the modeling of that is something that we've been able to do for a long time in terms of the different materials and the changes to those materials. But one really important piece that's been elusive over the years is the dynamic modeling aspect of this. So ideally, we'd be able to navigate through each of these spaces with these acoustic changes and then be able to select the different navigational tools that worked best for a given client. So in the past, what we've done is kind of stitched together various software packages to make this happen. And it's been successful, but it's a very laborious process of using different packages for different elements of this dynamic modeling to get, to be able to express the design changes that we're trying to communicate. Over the past couple of years, in the last 2 projects we've worked on with Chris, we have been able to develop a new method for dynamic modeling that's been much more successful. And I'll hand it back to Aaron to discuss some of the specifics.
Yeah, so the first project that I'll talk about with this is Guide Dogs for the Blind, their new campus in Oregon. And this is a training facility for guide dogs for the blind, and as well as an education and kind of residential place for these people to go while they're being paired and getting to know a guide dog. And this is one of the buildings that we've studied a few times where you've got a really long hallway that's kind of acoustically homogeneous, and you're worried about people trying to navigate through this hallway not being able to really track their progress through it. And so we can use acoustic wayfinding for this by varying the finishes along the wall, like Shane was talking about, and also varying the shaping of the wall itself. And so for guide dogs, we use Treble's oralizer the whole way through, and we simulated the dynamic walkthrough element of it by crossfading between different listening positions. And the main kind of win here is that we were able to really quickly iterate on designs and take direct output from Treble's oralizer, recorded into our computer, and then easily crossfading between those to get our sort of simulated dynamic walkthrough. And this was presented to the clients in our sound lab in San Francisco, and it was very effective. So then for the next project, where we had a really similar problem come up, this is the Indiana School for the Blind and Visually Impaired. They're designing a whole new education building. And they also had a long hallway where they were worried about students tracking their progress along. And so we proposed some similar ideas where you can have areas of absorption flanked by areas of reflection, and kind of trying those out in different spots in the hallway. And for this, we used one of our other modeling tools in conjunction with Treble. And so our other modeling tool is an acoustic solver for the Unreal Engine, which is used for video game production, as well as a lot of different architectural disciplines, visualization, data management, so on and so forth. And the benefits of using Unreal Engine and the acoustic solver for it is that you can do true dynamic walkthroughs. You can use an Xbox controller, or you can kind of preset your trajectory that you can play back for the client, and you'll walk through the space and you can see it as it's happening, and it's great. The main downside is that the acoustic solver plugins for Unreal Engine aren't usually targeted at our industry, and they don't usually achieve quite the level of accuracy that we look for. And so here we were able to use Treble to validate and calibrate what we were getting out of Unreal Engine. We could make the same model in Treble in an Unreal, see if we were hearing the same thing out of it. If we weren't, the Unreal plugins have some design controls that you can manually mess with to try to change the dry-wet ratio, change the reverberation time multiplier as a whole. And so we could dial that in to exactly perceptually match what we were getting out of Treble, which for an early design level oralization is absolutely sufficient. And the pros of using that dynamic walkthrough oralization technique were really, really compelling to the client. Again, they came into our sound lab. We had Chris Downey come in there as well, and he was really happy. The clients were really happy with the differences they could hear with the different design conditions walking through this hallway.
Thanks for watching. Once again, Aaron and Shane from Arup. If you'd like to contact us, our contact info is available. And
yeah, and thank you so much to the Treble team for putting this all together and for working with us on a great collaborative relationship on some of these features for their platform. It's been a pleasure. And thanks as well to L-Acoustics for presenting next.
All right, well, thanks so much, Aaron and Shane, for that very interesting presentation. I'm very happy to see that you guys are using Treble and getting some value out of it. And I really hope after today's big update that you will get even more value out of it. Okay, but I've already introduced sort of these big three new features: the BIM import, the modal analysis, and the source summing. And now I want to introduce a whole lot of additional improvements that we've been making. I sort of categorize them as quality of life improvements. I have a relatively long list here that I'm going to go through and obviously demo these things a bit quickly, but hopefully we'll get through all of it. First of all, we've sort of overhauled the look of the app a little bit, as you saw earlier actually, and we've sort of rethought the project hierarchy also, with the goal of making it a bit more intuitive and a bit kind of more seamless to work with. We have introduced this notion of being able to save states in the result view, so you can kind of set up some kind of result comparison, for example, and then save that and come back to that later or share that with a colleague. I'm very excited about this one, which is that we're introducing tutorials and learning content and validation cases and so on within the app, so that people can kind of expand their skill sets and understand the tool better and the technology behind, and kind of work with tutorials directly in the software and so on. Very cool stuff. we are accelerating the wave-based solver notably by allowing it or enabling it to be running on multiple GPUs in the cloud, not just one GPU as it has been up until now. This both means, in some cases, faster simulations, and it means that much bigger simulations, bigger wave simulations, meaning going higher in frequency and or bigger spaces, can be done with the wave solver. We are also introducing massive speed-ups, like order of 1,000 times faster, at least in some cases, for the GA solver, which is very cool. Some neat features to make the STI analysis more powerful, and especially make it kind of well suited for PA STI analysis. It's been an annoying issue in Treble that you could not place sources closer than 50 centimeters to walls. We've now mitigated that to a large extent. I'll show you more details later. And then in Treble, you can download simulation results in an Excel format, and we sort of added a bit to that to make it a bit more comprehensive. So these are a lot of kind of small but important improvements. Let's quickly take a look at them now. So the first thing we're going to look at is this overhaul of the UI and the kind of fine-tuning of the project hierarchy structure within the app. All of this work has been done with the goal of making it a bit more seamless to work with and intuitive. So if you're someone that has used Treble in the past, the Treble application, then you will note that this looks very different from what it used to look like. For example, this side panel here on the left is something we've added, which gives access to the home page, to my projects, to projects that have been shared with me, to these in-app tutorials. I'll show that in a second. Also the saved results and saved organizations and some assets as well. And then in the home page, I can see recent activities, so I can quickly get back to what I was working on, for example, the day before. This banner here pops up for new users, and once you exit, you won't see it again. It's just to help people get going. The project structure, so here I see my projects. If I go into a project, I will see different spaces. A typical example would be like a school, and then the spaces are the canteen, classroom 1, classroom 2, auditorium, etc. And then I go into those and run my simulations. And I can have different variations of materials and simulations and so on, but also of the geometries within that space. Okay, I think this, and then here is similar, just to the projects that have been shared with me, so not projects I originally created. I think I would next like to talk about this notion of a saved result. So let me show you here, if I go to a separate tab, here is a simulation I've been working on, or a results view. I've been analyzing this studio space to death, and I've kind of carefully set up this very cool view with all the main things I want to show and so on. And I need to go home at the end of the day, or maybe I want to share this with a colleague and have a review or something like this. Then I can now save this state as we see it here on the screen. I'll give it a name. I'll call it Studio Analysis, for example. And then it's saved, and I can come back to it later. And for example, if I now go back here to the results view here, you can see that this latest saved state in the result view pops up here. And here below we can see all kinds of results that have been saved, coming from projects that either I created or someone else created. Here's a project created by my colleague Auslaug, and I can, she was maybe wanted me to see some results in this space. Probably not, she was just testing something, but anyway, you get the idea. So this kind of notion of being able to collaborate and view results and review and so on. And this, of course, ties into the very fundamental cloud nature of Treble and this kind of collaborative workflows that Treble unlocks, where we can collaboratively work on projects. So I can, for example, the studio project I've been messing around with here today, I can simply click the share button here, and maybe I'll share this with my colleague Jesper. like so. Now he has access to the project as well, can run simulations in it, look at the results I've saved, and so on. So I think that was a kind of quick summary of the overhauled UI around the home page and this save state concept. I now want to go into these tutorials. The amount of content in there is not so much yet, but the whole kind of system has been built, and now we will be rapidly adding more and more content in here. But the system is really cool. So here we can see different types of tutorials that will be populated in here. It will be all kinds of tutorials around operating the tool, but as I mentioned earlier, also validation cases and benchmarks and interesting phenomena of acoustics that you can look at and so on within the tool. And if I open a tutorial here, this is a tutorial about summing sources, which is a feature I was illustrating earlier. Then what happens is that I go into a project which already has a lot of simulation results, and there's an accompanying tutorial here which kind of shows how the whole thing was set up, how it was done, what needs to be thought of when looking at the results, what are the limitations, blah, blah, blah. All of it is kind of in here. I can walk through it. I can look at the results in the same way as the tutorial shows. And I can, because once I open a tutorial, it actually gets copied to my projects. So I can continue working with this and maybe run a different simulation or change some parameters from the tutorial and see how that affects the results and things like this. So I think this is something that will empower users to become more skilled in acoustic simulations and working with the software. Very exciting. So this was the tutorials and the app overhaul. Let's now turn our attention to the acceleration of both wave and geometrical acoustics. Okay, so the next topic is about multi-GPU acceleration for faster and or bigger wave-based simulations. So up until now, the Treble application has only leveraged one GPU per simulation, but now we offer the capability to leverage several GPUs per simulation. And this kind of handling of how many GPUs are per job is taken care of for the user, so just kind of the optimal amount of GPUs for a given job is selected automatically. Now the kind of whole science around parallel computing and all that stuff is quite complex, and I'm not going to dive into all of the details here. So it can be a bit nuanced in kind of how much performance boost one gets in what types of cases and so on. It's not just some very simple linear curve or something. But overall, I think the takeaway is that for small wave-based simulations, that's either small rooms or at low frequencies, there is actually no difference between running a single GPU versus multi-GPU. So the software will actually just select one GPU for such small jobs. Then we have a category of jobs which is sort of medium-sized jobs, you can say. These are jobs that you could run on one GPU, but leveraging more than one GPU speeds the simulation up. And then at a certain point, the simulation gets so big that one GPU cannot handle the job. It simply cannot fit all the mesh elements in the simulation into the memory of the GPU. And this is what the third category, let's say large jobs. And then you need many GPUs to be able to run such simulations. So in summary, small jobs, no difference. Medium jobs, faster now than before. Big jobs, possible now, weren't possible before. And I'm going to illustrate this with a case, which we see here on the screen. This is a sort of relatively large auditorium. It's around 18,000 cubic meters, so quite a lot of volume. And I've simulated this space sort of before and after we introduced this multi-GPU functionality. And I'll show you some performance numbers and so on, but just showing you first here that if you are in multi-GPU territory, then you are notified of this when you hit the run button here, that multi-GPU is enabled. So you are benefiting from that functionality. But let's take a look at some performance numbers for this hall here. So I'm going to switch over here. The hall has been simulated for a few different transition frequencies with and without this multi-GPU functionality. And if we first look at the kind of lower transition frequencies, this is the upper limit of the 125 Hz band, and this is the upper limit of the 250 Hz band. Then we see that multi-GPU does not actually lead to performance increase, so this job runs most effectively on a single GPU. However, if we come up to 500 Hz for this 18,000 cubic meter hall, without multi-GPU, the simulation takes around 90 minutes, but with multi-GPU, only 58 minutes. So this is a notable performance improvement. If we then go beyond 500 Hz, I think only around 550 or something like that, we are actually out of range for a single GPU. The memory is full, so you can only go up to around 550 Hz or something like that with a single GPU. But here I show going up to 800 and 1200 Hz. And we see, of course, these simulations take longer. This is going quite high in frequency for a very big hall, but it's certainly still doable. And this is something that you could not do before. And you can, of course, leave this running overnight or work on other things while this is running in the cloud, and you can run many simulations in parallel and all that. So this is a very nice improvement regarding the wave-based performance via multi-GPU. Next on the agenda is acceleration of the GA solver. We have essentially rewritten notable parts of both the image source solver, which is for early reflection modeling, and the ray tracing solver, which is for late reflection modeling, so that it performs much faster than before, especially in complex geometries where we see several orders of magnitude in speed up compared to what we had before. So now you can, with Treble, very easily simulate very complex models with geometrical acoustics, which was difficult to do before. And I'm going to show just a couple of comparisons running side by side, essentially before and after this performance upgrade. First, sort of a relatively simple model, the one I have on the screen actually right now, where we see sort of a modest performance improvement. And then I'll show a more complex model with a lot of small surfaces, a lot of curved surfaces and so on. This also reminds me that Treble kind of very much handles curved surfaces very well, so you can have very finely meshed curved surfaces, and all solvers handle that very well. Okay, that was the GA speedup, which was quite notable, as we saw, especially in that complex hall. Now we are going to talk about three small but nice improvements. The first one has to do with STI Analysis, Speech Transmission Index, where we have now enabled users to control the sort of sound power or sound level that comes from the source used in an STI analysis, which means the main benefit or use case of this is that you can analyze speech transmission, speech intelligibility from PA systems. So here on the screen I have open source settings for actually just an omni-source, which is by default calibrated to be around 103 dB on axis at 1 meter. I've put gain here to reduce the level by 30 dB, so it's at 73 dB on axis at 1 meter. If I'm looking in the same model here, and I'm in the results view, and I'm looking at the STI, then what's new here is the ability to either select speech spectrum according to ISO 3382-3, that's around 54 dB on axis if memory serves me right, or I can select the SPL level that was set in the source. So you can have a PA system with a certain level of gain or a certain sound pressure level that the system is playing, and then you can analyze the speech intelligibility as a function of background noise levels, the NC curves here. And you can, this is just for a point receiver, you can obviously also do this for a surface receiver and all of that. Next up is a nice improvement which has to do with the ability to place sources close to walls. So before in Treble, there was a limitation that you could only place sources 50 centimeters away from the wall or further. And this is due to the way sources or sound is essentially injected into the wave-based simulation. There's kind of a pressure balloon that takes up some space, which we need to put into the wave-based simulation in order to run the simulation. But the block that we had put to kind of ensure that this was okay was a bit over the top, let's say. So now we have adjusted it so that, first of all, for GA-only simulations, you can place sources anywhere, no limitations on that. Secondly, for hybrid or wave-based simulations, this block of how close you can place the source is actually frequency dependent. So if you go higher and higher in the wave-based simulation, the source gets smaller and smaller, so you can place it closer and closer to a wall. Let me show you here. This is the studio model we've been playing around with. I have a transition frequency of 700 Hertz. I believe that means that the source can be placed up to 10 centimeters away from the wall, as opposed to the 50 centimeters from before. So if I just try to move this one here up against the wall, oops. Okay, you'll see here it's kind of exactly on. So this is too close. But if I just move it a little bit out, you see here, I can place it quite close to the boundary now, up to 10 centimeters. And if I would go up to 1500 Hertz in this simulation, I could place it 5 centimeters. If down to 355, which is the 250 Hertz octave band, then I could place it 20 centimeters away. So you can, and this is obviously, these kind of details are available in the documentation. Long story short, GA sources anywhere, wave-based sources closer than before, and especially if you go to relatively high frequencies, you can place it very close to a surface. I hope that's a nice improvement for our users. The final thing of this long list of kind of quality of life improvements is that this Excel sheet that you can download when you are in a result view. So here I'm in the studio and I can download either the impulse responses or an Excel sheet which contains all the parameters from the simulation. If I do download that and open it here, then we've added this setup sheet here, which kind of contains a summary of the simulation in question, along with then all the results that were in there before. So this can be a way to kind of, if you want to document your simulations in a kind of store it somewhere locally or something like that, then you can do that by downloading these Excel sheets, which contains the setup in question. I do mention though that all the data is stored and backed up very securely and stored for eternity essentially, so you don't need to worry about your data being stored in Treble. That was it for the quality of life improvements. Now we're going to give the word over to L-Acoustics to see their very interesting presentation, and then I'll wrap up with a couple of quick updates after that.
So hi, my name is Simon Brown. I am the Technical Product Manager of Acoustic Solutions here at L-Acoustics. L-Acoustics have been at the forefront of loudspeaker design for the past 40 years. Our sound systems can be found in venues and on tour all over the world. We are the pioneers of the line array technology, which was driven by the sole aim of providing a high quality and consistent sound experience to all over the audience. In more recent years, we have developed our ELISA technology that with increased loudspeaker configurations and our object-based mixing algorithms can provide a heightened sense of realism. And also with loudspeakers around the audience and overhead, we can provide a more immersive sound system which provides greater creative control for sound engineers and creatives. So all of our innovations have been driven by the sole vision of creating a human connection through sound. The power of a live event is in that sense of connection, and we believe that high quality audio can evoke a unique emotional response that is key to bringing experiences and live events to life. So in recent years, we have broadened our focus, not just from the sound system, but to the room itself. A sound system does not work in a vacuum. The room is a critical component to one's response to a live performance. And I've worked for many years as an acoustic consultant before joining L-Acoustics, and my role here is to sort of fully understand how a loudspeaker system and the acoustics of a space can work together to provide the best possible experience for audiences and for performers. In order to do this, it is key that you have a good understanding of the acoustic properties of a room, and Treble is a fantastic tool for being able to simulate how a room will respond to a sound system. So our hyper-real immersive sound spaces, or HYRISS, aim to bring this concert-grade audio to a much smaller scale, be that the home, hospitality, or a corporate setting, for example. It consists of a 3D network of loudspeakers on the walls and in the ceiling, and this allows you to have ultimate flexibility for how you use sound within your space. This could be a movie with a Dolby Atmos soundtrack. It could be a stereo track that you could pan to any place within the room, or it could be a fully immersive audio track that completely surrounds you in sound. Also, with our active acoustic system ambience, this allows you to adjust the acoustic energy within the room to meet the need of the event. This could be if you have a party, for instance, you can increase the sense of acoustic energy within the room. If you had a conference or a voice event, it would allow you to boost the clarity of speech. Also, if you had a music rehearsal, say, or a piano recital, for instance, you could extend the reverberation time to bring out the best in the music for the audience. Our HYRISS showroom, which is in Highgate in North London, is a room which is approximately 80 square metres in floor area with a ceiling height of between 3 and 4 metres. It has 16 loudspeakers on all 4 walls and 12 speakers overhead. As you can see when you look around the room, you cannot see where the loudspeakers are placed. They are perfectly integrated with the architecture of the room, hidden within recesses within the walls and the ceiling. This integration with the architecture is a key aspect of HYRISS, and it extends not just to the architecture, but to the lighting control and design and the rest of the AV systems, and also includes the acoustics. The acoustic aim of this space is to provide a controlled acoustic like you would have in a studio. This allows the sound of the speakers not to be coloured by the space overly when you're in a setting for cinema or for high critical listening of music, for instance. But we didn't want the space to be so dead that when you were in it in a home environment or just naturally in the room that it felt oppressive. And also wanted enough natural acoustic energy within the room that for our active acoustic system to operate, it could then effectively regenerate this natural acoustics of the space. So we had a target of reverberation time of approximately 0.4 seconds was our aim, and we wanted this to be flat over the audible frequency range as low as possible. The low frequency performance is key for a loudspeaker system, and in a room of this size, room modes could lead to potential inconsistencies in the room response. And we wanted to understand this, and we believe that Treble's wave-based algorithm would be a very useful tool for understanding this and helping us make the right design decisions. So our design for the showroom started, as most acoustic designs do, with a 3D model. This was done within SketchUp. Importing this SketchUp model into Treble was very, very pain-free. There's a useful plugin for doing this. It also provides very useful feedback onto the integrity of your model, so you can easily visualize any potential errors. This was a very pain-free experience. Our next step was to carry out acoustic measurements in the untreated room. This allowed us to calibrate the initial acoustic model to understand the acoustic properties of the residual surfaces, such as the plasterboard walls and the floor. So we could create new materials within Treble very easily with their material builder to adapt to these measurements and to ensure full accuracy of the acoustic model. Once we did this, we were then able to trial our different design options with thicknesses and location of absorption. It became quite clear that we initially didn't have enough area. We were contending against large reflective surfaces such as our AV screens and the sheer number of loudspeakers. We needed to find some additional area to bring the RT down to its design target. We were able to find this in areas high up on the walls and the ceiling. and this proved very effective. Another design concern was that of flutter echoes. We have large AV screens in a room with a very low RT, so this was a potential problem. But luckily, with the use of Treble's reflection tracker and with the auralizer and the hedgehogs, we were able to assess different loudspeaker positions, whether they would cause any flutter echo issues, and we came to the conclusion with a good degree of confidence that actually this wasn't going to be a problem in this room. The result is a space of the highest quality and really shows the possibilities of how you can integrate a high quality sound system with the architecture, with the lighting, with the AV and with the acoustics of a room. Treble was a key factor in the design of this space, and particularly understanding the acoustics performance at low frequencies. As you can see when you compare the measurements of the finished result with the Treble prediction, the accuracy at low frequencies is vastly superior to that of a basic geometric modeler, and this was crucial for us understanding what we needed to do to make the space the best place it could be.
Okay, wow, thanks so much for that amazing presentation from Simon from L-Acoustics. That was really impressive. I really want to go to that showroom. Anyway, two things, a couple of words about two new exciting partnerships between Treble and some industry leaders. And then a quick word about our updated licensing model. We've made some changes to try to make it more attractive, more transparent, and so on. And then we can open up the floor for Q&A. So the first partnership I want to tell you about is between Treble and Saint-Gobain Ecophone. Ecophone is one of the biggest manufacturers of acoustic materials, suspended ceilings, wall panels, and all kinds of products relating to controlling sound in space. And we are collaborating with them actually on several fronts, but perhaps one of the more interesting ones is that we are developing ways to characterize absorption properties in a more precise way than the kind of standard ISO 354 reverberation time absorption coefficients approach. And the goal here is that all Ecophone products will be featured in Treble, and they will be characterized in a more precise way using either impedance or flow resistivity or something like this. This is still under research. So that people can use those materials in the material database and essentially model or sort of reduce the uncertainty relating to the material properties, which is of course one of the biggest uncertainty factors for room acoustic simulations. We're taking these first steps with Ecophone, but of course we want to spread this approach wider and ultimately provide users of Treble with accurate material, or let's say more accurate material data than what has been previously available from all kinds of manufacturers in the tool, and kind of trying to move the industry in an exciting new direction regarding characterizing absorption properties. Because the solvers themselves in Treble really can deal with very granular material properties, so it's a matter of getting that data in there. Very exciting stuff. Stay tuned for more. The second partnership I want to mention is between Treble and L-Acoustics. L-Acoustics is one of the most prominent sound system manufacturers on Earth, and we are very proud to be partnering up with them. And together with them, we are going to develop or co-develop sound system modeling technologies, and we're going to make them available to Treble users and L-Acoustics customers to enhance capabilities and sort of introduce integrated workflows to ultimately help people design sound systems and kind of the interaction between sound systems and spaces in a better way. So please also stay tuned for that. Very exciting stuff. Final thing here, the licensing model for Treble, we've taken a spin on that. We used to have this notion of a compute token before, where simulations in the cloud would essentially cost tokens. Users would buy tokens and then spend them when using the tool. We got some feedback from the acoustics community that this was not optimal in some ways. It was kind of hard to predict what the bill would be, and overall the model just didn't scale maybe very favorably for at least some users. So we have updated our licensing model. I'm not going to go into the nitty-gritty details of it, but just the high-level summary is that we have three brackets: single user, teams, and enterprise. And then within single user and teams, we have both a standard tier and a premium tier. The premium tier includes a bit more powerful analysis capabilities and also more powerful cloud computing included, whereas the standard tier has a bit less of that. Enterprise, on the other hand, is completely custom, or it can be tailor-made to any kind of requirement. And we hope that this model is well received by the industry, and that we've really tried to strike a good balance between making a model that is easy to understand, that is predictable, and that is kind of scales well with different team sizes and different budgets and so on to accommodate all user types. And on that note, I also want to just end here by thanking the acoustics community for their support and their feedback and their enthusiasm around Treble. We really appreciate that, and as I said in the very beginning, Treble is a passion project. We are trying to build some great tools to help and serve this community, and we look forward to continuing the dialogue with you all, and welcome all suggestions, and just, yeah, hope to work together to make the world a better sounding place. Now, it's time for some Q&A. Thanks, everyone.